So the first paper is the boombox view reconstruction from acoustic vibrations. And Boyuan will present the paper.
Hello, everyone. I'm Boyuan Chen, and I'm a PhD student from Columbia University. Today, I'm excited to present our work on the boombox visual reconstruction from acoustic vibrations. This is joint work with Mich K, Holt Lipson, and Carl van Drake. Majority of human sensing comes from our visual perception system. With recent progress, machines can also perform various tasks from visual signals. However, this is not the full story. We also heavily rely on other sensing modalities in our daily lives, for example, audio signals. Through the sound made by a falling coin, we can localize the coin. Similarly, we can tell that a car is approaching through its sound. Although current computer vision systems may achieve high performance in these tasks with a high-speed camera or video footage covering the entire environment, it remains challenging on how to understand the visual scene when the informative visual signals are occluded or completely missing. In this research, our key hypothesis is that audio signatures in such events can help uncover the visual contents under these difficulties. Our research studies how to generate visual scenes from acoustic vibrations. A minimum example is a container as shown here. If you drop an object into the container, the object will bounce around inside the container with very chaotic trajectories. However, what is happening inside the container is fully occluded from the current camera view. This makes it very challenging to predict the scene inside the box. To resolve this challenge, we present the boombox, a smart container that uses acoustic vibrations to reconstruct an image of its inside contents. We equip the boombox with 4 low-cost and low-power contact microphones. Acoustic vibrations provide a different modality when visual signals are not available. However, due to the fast speed of the sound transmission and subtle but critical features in audio signatures such as volume or time differences from multiple channels, traditional hand engineering techniques may have difficulty to provide accurate estimation. Plus, when different objects interact with the container, various shapes of the objects are hard to recover. To this end, we propose an end-to-end learning framework to generate visual scenes from acoustic signals alone. The training process of the boombox starts from a self-supervised data collection. First, we put a top-down RGBD camera to look inside the box. By randomly dropping 3 wooden blocks with various shapes, we can obtain a dataset of the acoustic events along with the final visual scene. These 2 signals compose the entire training data. Here, we show some examples. During test time, by taking only audio vibrations as input, the boombox can predict the final scene inside the container by directly outputting an RGB or depth image. Here are some examples. On the left, we show the input audio spectrograms from the contact microphones. By overlapping the predicted RGB and depth image, we can also view the prediction as a point cloud as shown here. Further visualizations of the learned features show that concepts such as position and orientation of the objects emerge automatically through the learning process. Our study presents an integrated hardware and software platform for using acoustic vibrations to reconstruct the visual structure inside containers. We find that acoustics are pivotal for revealing the visual structure behind containment. We hope our research can open up new opportunities for multimodal perception and robotics. For more information and open source the codebase, please visit our project website. Thank you.
Please post any questions you have on the paper in the Zoom chat. I'm referring to paper 1.
Hello, everyone. I'm Boyuan.
So the next paper we have is called Visually Informed Binaural Audio Generation Without Binaural Audios. And the presenter is Xudong Xu.
Here, we present visually informed binaural audio generation without binaural audios. In this work, we focus on the task of visually informed binaural audio generation, which converts the input mono audio to the binaural audio with information of its corresponding videos. For this task, the supervised measures have to chain on visual stereo pairs, namely binaural audio data and the corresponding visual scenes. However, this paradigm requires professional recording devices to collect the binaural audios. Here, we have a proposal. How about using mono audio data, thus getting rid of these professional devices? Our key insight is to carefully build pseudo-visual stereo pairs with mono audio data to get the chaining. For creating these pairs, we propose two mappings, Mono-Binaural Mapping and Visual Coordinate Mapping. Mono-Binaural Mapping is to transfer mono audio to binaural audio. Specifically, the mono source is assigned at a random 3D position, and then, through spherical harmonics decomposition of the source, we take the zero and first order components to form the ambisonics. Finally, we will decode the ambisonics to binaural audio in this step to make up the reverberation in the real scenarios. We specially decompose the ambisonics to several virtual speakers, and the sounds from these speakers will be converted to binaural audio with HRIR, head-related impulse response. Furthermore, we use visual coordinate mapping to create pseudo-visual scenes. Specifically, the front view image plane is defined as part of a cylinder centered as the coordinate origin. Empirically, we set the horizontal visual field of view to 120 degrees. Note that the center position of a visual patch must be aligned with the assigned position of its corresponding audio in the previous mono-binaural mapping process. For the learning, we adopt similar network architectures as the baseline methods. We apply a UNet for the audio and a ResNet for the video processing. The input is the spectrogram of mono audio, and the network aims at predicting the spectrogram difference between the left and the right channels. Apart from this, we actually incorporate audio separation tasks to guide the chaining, and find it will lead to better performance on binaural audio generation task. To validate our proposal, we conduct experiments on two large-scale datasets, Fairplay and Music Stereo. As shown in the table, our approach, pseudo-binaural, is able to generate good binaural audios by chaining on pseudo-visual stereo pairs. Moreover, pseudo-binaural can boost traditional supervised methods with stereo training data. Our approach consistently outperforms baseline methods on 5 different evaluation metrics. In the cross-dataset evaluation, our approach avoids overfitting to a specific domain and demonstrates better generalization ability than the supervised methods on all datasets. In the meantime, users slightly prefer our approach over supervised baselines. As illustrated in the activation map, we focus more on sound sources, not the maintenance background. For more demo and the code, please refer to our project page or GitHub repo. Thank you very much.
So the next paper is on sound localization. It's called Unsupervised Sound Localization via Iteratively Contrastive Learning, and Yanbo will present the paper.
Hello everyone, my name is Yanbo Lei. Today I would like to introduce our work, Unsupervised Sound Localization via Iterative Contrastive Learning. Sound localization is aiming to localize sounds in the visual scenes. For example, when you see a car and hear its engine sounds, we would like to localize the car in the visual scenes. That is expensive to annotate the sounding region. That is because we have to see and hear simultaneously. Thus, self-supervised and unsupervised methods are proposed. If image and audio sample from the same video clip, they are positive pairs. If they are sampled from different video, they are negative pairs. Based on this assumption, we can localize the sounds, but the localization result is not very good. So, starting from the conventional contrastive learning, our method can use the cross-prediction result to find pseudo-sounding regions and pseudo non-sounding region. And there is an issue for conventional contrastive learnings. It assumes that image and sound from different video clips are all negative pairs. But in some cases, like there is two trends in a batch, they should be positive pairs. And that is our train pipeline. In current training epoch, we take the result from the previous training epoch. And there is two modules. First one is our proposed intra-frame sampling module. And second one is the inter-frame relation module. In the intra-frame sampling module, we're sampling a pseudo non-sounding region and a sounding region. And at inter-frame relationship, we use audio relationship to determine which pair is positive pairs and which pair is negative pairs. Well, starting from conventional contrastive learning, we would like to maximize the similarity between audio and visual features from the same image pairs and minimize the similarity from different pairs. So in intra-frame sampling modules, we take the result from the previous epoch, then we set a threshold to find the potential sounding regions. And also, if the score is lower than the threshold, these patches may be non-sounding regions. So in our interframe relations modules, there is a K audio instance. So we measure the similarity between each instance. So if the similarity is higher than the threshold, the pair would be the positive pair. Otherwise, it may be the negative pairs. Then that is our loss. That is aimed to maximize the similarity between sounding regions and its sounds, as long as they are positive pairs, and also minimize the non-sounding regions and the audio visual feature from different pairs. We evaluate the two benchmarks. One is SoundFlick dataset, and the other one is music synthetic dataset. The SoundFlick dataset that is a wide range dataset. It contains different objects, and the music synthetic dataset it contains two sounding instruments and two non-sounding instruments in the visual things. So in these both dataset, we can outperform the stale-filia method. And that is our visualization result. The first two rows is in the SoundFlick dataset, and the remaining two rows is in the music synthetic dataset. That is our demo video. And thank you for your listening.
Yeah, please post the questions for this paper in the Zoom chat area and refer paper 3. And we have a last paper in this paper
Hello
Google
everyone.
Consensus.
My
The
name
next
is
one is called See, Hear, Explore, Curiosity via Audio-Visual Association. And Victoria will present the work. Victoria is not available here for Q&A, but she's happy to answer any questions offline.
I'm Victoria Dean, and this is work done with Shubham Tulsiani and Abhinav Gupta at Carnegie Mellon and FAIR Pittsburgh. In this work, we present See, Hear, Explore, a new curiosity formulation using multimodal self-supervision. In the standard reinforcement learning setting, we have an agent taking actions in some environment, and then receiving the resulting observations. The question for reinforcement learning is, what actions should the agent take? A common answer is to optimize an agent policy with respect to extrinsic rewards. Prior work commonly optimizes for extrinsic rewards, which can be hand-engineered to suit the current task. However, life doesn't give these dense rewards. As we move to longer horizon tasks, engineering extrinsic rewards will become more complex. We want agents that can explore and act with less supervision. Instead of using extrinsic rewards, an agent can create some notion of an intrinsic reward and use this to explore without supervision. Then the question becomes, what is the intrinsic reward? We note that observations are not just a single stream of information. We're motivated by research in child development, which has found that babies explore by making use of many senses, including vision, audio, touch, and even taste. We want an intrinsic reward that similarly leverages multiple modalities, allowing agents to exploit the richness of our physical world. One existing formulation for intrinsic reward is prediction error, in which a model predicts the future state from the current state. A multimodal interpretation of this intrinsic reward might be cross-modal prediction, such as predicting sound from an image. However, this definition would still struggle in stochastic settings, such as pushing a button that randomly plays one of two sounds. Instead, we look at association, asking a simpler question. Can this image co-occur with this sound? To train the association model, it's clear that we can get positive examples from the episodes themselves. We feed in co-occurring frames in audio, and a discriminator learns to output yes for these inputs. But how do we get the negative examples? We construct these negative association examples by shuffling the audio. With these misaligned examples, the discriminator is trained to output no. These positive and negative examples create a binary classification task. We also weight the negative examples by the difference from the true audio. We learn this association model online during exploration. The agent might encounter an audio-visual association that it has not yet learned, in which case the agent receives reward for uncovering this novel association. Here we show qualitative examples comparing our method with curiosity via self-supervised prediction. Notice the baseline agent on the left moves the paddle rapidly, as this stochasticity is hard to predict. On the right side, our agent explores what happens when bricks from different levels are cleared. Here we evaluate quantitative performance using the extrinsic game reward as a proxy for exploration. Our association-based agent explores more efficiently in 8 of these 12 Atari environments. Even more promising is the performance on a realistic exploration task, indoor navigation using AI habitat. In this simulator, audio is emitted from a source. The agent moves throughout the scene, again with no extrinsic reward. The agent sees an egocentric image and hears the audio from the source. Different agent locations lead to unique sounds due to scene geometry. On this task, a more successful agent will achieve more uniform coverage by visiting rarer areas more frequently. Here we plot the state visitation counts across the first 2,000 training episodes, sorted by frequency and shown on a log scale. The most common states are on the left, while the tail of rare states is on the right. See Hear Explore, shown in blue, visits more states more often, representing more efficient exploration. In conclusion, we've seen how we can use multimodal associations for better exploration. All of our experiments are using vision and sound, but we think the method holds promise for use beyond these modalities and look forward to future work in this area. For the full paper and code, please see our website. Thanks.
Okay, that's the 4 papers for this first paper, invited paper session. So thanks for the 4 presenters who presented work in different sub areas of audio-visual learning, very exciting work. So if you have any questions for any of these 4 papers, I think for the first and the third paper, Boyuan and Yanbo are both here. So feel free to ask any questions in chat, or feel free to unmute yourself to ask questions directly. I think Valentina asked a question for paper 2, but unfortunately the author is not here, but he's happy to take the questions offline. So to get started, I think maybe I can ask a question for Boyuan. So
yeah, please go ahead.
Yeah, I think it's very cool work. Yeah, it can reconstruct the 3D shapes of objects just from some contact microphones. So I'm just curious about during training, are you training on the same set of object shapes, or can you train on one object shape and generalize to other object shapes? I'm curious about, is there any generalization across different object shapes, or more, household objects often contains very diverse object shapes. I know you're learning from blocks, but do you have some preliminary observation that it can generalize across objects?
Yeah, so that thanks for Hansel. I think that's a very good question, and so maybe I can try to answer your questions from 2 different angles. So first of all, the particular focus for our current work is that we don't really study the generalization across shapes. And one of the main reasons is because we don't really have that many shapes in the data set. And because of the difficulty of collecting the data set, we need to drop the different shapes into the box and collect all these visual and audio data set at the same time in the real world. So, it's quite challenging to have 100 different shapes that will study this. And also, the data set collection process happens during the pandemic. So it's kind of hard to collect really a lot of data set. But that's something we were also curious to know, if the data can generalize across multiple different things. And another angle is that, but in terms of generalization, actually, we do see generalization across different initial conditions. For example, if you drop different objects with a different initial pose, then you can tell actually, what is the object you're dropping by synthesizing the correct shape correspond to it. And a different angle to answer your question probably is to start from a failure mode. The common failure mode we observe from the experiment is that if we drop, say, the long stick of the object, and if we drop another one that is slightly thicker than that, but still a rectangle kind of shape, sometimes the model will confuse in between of these 2 different shapes. And one potential reason is because all these are kind of cubic type of shapes, so it looks very similar. Especially the bouncing tells you most likely about a lot of information about the shape and the position and dropping velocity and trajectories, but it still have this ambiguity, which edges it's dropping. And especially for this long stick, because the purely natural real world data set collection process, sometimes it even stands with a very the small area face. So that will also create a lot of distinctions even within single shapes. So from our current observation, I think it still have some ambiguity. So if you want to generalize across different more shapes, you probably want a diverse set of shape that will have different primitive in terms of in shape geometry. And so that's one. And the other thing is that currently our feeling is that you might still have difficulty to generalize across very diverse set of shape with a small sample of training shapes. So, we hope that if we see a larger data set on the same version, maybe we should be able to generalize on different, on more type of shapes.
Yeah, very cool. I think definitely it's a very challenging problem to just to do 3D reconstruction purely from audio.
Right.
Maybe a follow-up question on that. So do you think how important are these? I know you place 4 contact microphones in the box, right?
Right.
How important are the locations of the contact microphones or a number of contact microphones? Is that important for you to do the 3D reconstruction?
Yeah, that's a great question. I think, to study the arrangement in terms of how to place the sensors when you're recording, audio is definitely one of the most exciting direction along this area. And I think in our experiment, we didn't really try to design in terms of where we want to place the shape. And even the position of the contact microphones are not really designed by us. We just randomly put on the 4 faces. And even the training data, we never know like the exact physical location of the contact microphones. And the only time where we try to measure the location of this, and we find that is sensitive, is that when we try to run baseline methods, where you try to use time difference variable to calculate how sound transmits within the box. So in that case, it's relatively sensitive in terms of like traditional baselines. But that's kind of the advantage of using the learning-based method, where the model could potentially capture the location of the contact microphones implicitly inside the learning. And on the sensor node, what's important actually is the contact microphone, like design of using contact microphone. While I was collecting data, my cats were like running around in the room, and my wife was clicking on the keyboard, but you don't really hear all of this. None of this you can hear in the data set. And that's like advantage of using contact microphone, that it can capture all these vibrations caused by this physical contact between the object and the box. But if you use like an air-based, sound transmission, say air microphone, then probably you're going to hear a lot of noises that you want to filter out. And probably these noises are not also necessary to tell you like how this interaction between that particular object with the box. Yeah, so that's kind of our experience in terms of the hardware.
Yeah, thanks for answering the question. I think there's a kind of similar question, a follow-up question from Valentina. So have you estimated the accuracy in position and orientation? And what about using 2 microphones? Maybe you have already answered some of them, but yeah, you can elaborate a bit more, that'd be great.
Yeah. So I think there are 2 questions, right? The first one is estimation of accuracy in position and orientation. So in our experiment in the paper, we do have accuracy in terms of measuring the intersection over union, and also the something we call a success rate, but like really a localization metric. So what we do is that after we train the model to synthesize the RGB and depth information, we can crop the image by just doing a simple background color subtraction, and you can get the bounding box of the object. But of course, all these are only for evaluation. And after we do that, as long as the predicted bounding boxes is within the range of half of this, half of the diagonal line of the entire shape, we call it like successful localization metric. And we find that our method actually achieves pretty good accuracy in terms of the localization metric. And one of the inspiration of evaluating the position and orientation with both IOU and the localization metric is that this task, when we designed it, we had potential applications of robotics application in mind, where if we have say a suction robot gripper, and after you drop something into the box, due to different lighting conditions that you might not be able to see, or occlusions in what's inside the box, this metric basically will give you the point where you want to have your robot gripper to navigate to inside the box to pick it up. So this will be very useful for downstream applications in robotics. And the second question is about what about using 2 microphones? So that's a very good question. Our hypothesis is that probably you're going to only need 3 microphones. And that's really based on the theory of sound transmission and the localization, where in a traditional setting, if you have only 2 microphones, it's kind of like the cases where you only really get the depth information. Like if you think about the depth camera in vision, you really need 2 set angles. But in sound, remember in our case, it's really a 3D environment. It's inside the box. Different shapes may fall behind. If say the pen might fall like this and might fall like this, and sometimes you kind of hang around on the corner of the box. So it's like a very diverse data set that have like 3D spatial location. And in that case, you probably need at least 3 microphones. And we just have 4 because the box have 4 faces. But we really didn't really try to design like, how accurate you should place all these microphones around the box.
Yeah, thanks, Florian. Very cool. Yeah. Maybe have one question for the 3rd paper on sound localization. So for Yanbo, so I know it's you are doing sound localization in video frames, and I was just wondering, have you considered any off-screen sounds? Do you have any thoughts about off-screen sounds in this case? There are some sounds that can be audible but not visible. Some sounds that be visible but not audible, and also there's cases like the sounds that. The sounds and the video event, the event is both audible and visible, right? So I wonder, just in your experiments, do you have explicitly studied something like that, or what's your thoughts about this off-screen sounds that will affect sound localization accuracy?
Thank you for your question. Yeah, I think for most of the audio-visual data set, the audio may contain in the visual things. But if we try to train this kind of method with audio and visual, which is they are not pairs, we may not achieve this kind of result. That because we all have to assume that most of the data are pairs, but if some data is not paired, it is okay because it is not the majority in the data set.
Yeah, got it. Thanks. Any other questions from the audience? Feel free to unmute yourself to ask questions. So if not, thank the first presenters again. And if you have any questions, please feel free to email the presenter, and they're definitely very happy to answer your questions offline. Yeah, thanks again for the 4 presenters in the first group of papers. So next we'll have another 4 invited paper talks about different areas, different tasks in audiovisual learning. Let me share my screen again, and we can listen to their talks.
I'm Victoria Dean.
So the next one, the first paper in this session is called VATT, Transformers for Multimodal Self-Supervised Learning from Raw Video, Audio, and Text.
Hi everyone, this is Hassan from Google, and I'm going to present our recent work on multimodal transformers with our collaborators at Google and also Columbia. So the research question that we are trying to answer in this paper is, can we have one architecture to learn multimodal representations? And if so, can we share that architecture as one backbone across different modalities? Also, can we operate on raw inputs, and can we tune this model to accept raw inputs, and how we can deal with redundancies? And the last question, which is also the most important one, is can we train this pipeline end-to-end without supervision? So there are a few related work in the literature. At the time of the publication of this paper, there were no audio or multimodal work, and there was only one video work using transformers for representation learning, and a few works on image, but all of them were using basically large-scale supervised pre-training for training an entire transformer end-to-end. So we introduced VAT, which is basically video, audio, text transformer, and this paper is publicly available. So we focus on modality agnostic architecture, and we want to also share that architecture across different modalities, which we call it modality agnostic weight or modality agnostic setting. And that supports high resolution inputs, and it outperforms the state of the art in a variety of downstream tasks. And most importantly, it operates on raw inputs. So the pipeline is pretty straightforward. We have raw video, waveform, and string text. And we have a very minimal pre-processing and homogenization where we extract different patches and apply a linear projection on those information. So for video, is 3D patch, which is voxel. For audio waveform, and also for text is temporal patch. And we encode a raw input to a sequence of vectors, and once we have a sequence of vectors, we use a transformer encoder to extract semantic features. So once we have the semantic features, we use a contrastive estimation to minimize the cross-modal correspondence loss. And we have a modality agnostic setting that we combine and merge all those transformer encoders into one single transformer. So we have a modality agnostic model that operates on different modalities, but it has only one set of weights. So it has 3 forward calls, but it has only one update. And it uses the same contrastive estimation as the modality specific one. So the contrastive estimation is basically minimizing the noise contrastive estimation between video and audio features in a common space, and also minimizing the MIL and CE between video and text features in a common space, which is a pretty common contrastive learning pipeline. So we pre-train our model on large-scale data sets, 500 million an audio set. We basically combine them and sample from them equally, and evaluate this model on a variety of downstream tasks, including video action recognition, audio event classification, image classification, and zero-shot video retrieval. We see that on video action recognition, our model basically outperforms all previous methods, including CNNs and transformers. And a big difference is that we use a plain transformer. We don't have any custom architecture, and we have a self-supervised pre-training. And we also have a modality agnostic weight. So, so this model is kind of pretty different from the previous efforts on transformers on video. And on the audio event classification, we see that the model successfully outperforms all previous methods that do audio event classification on audio set using CNNs on raw waveforms. Interestingly, we see that in spite of having a domain gap, the model, if we fine-tune it on image classification tasks, we still see that it achieves a comparable number to VIT, which is trained on pre-trained on JFT with a self-supervised objective. And we finally see that if we freeze the model and just do a zero-shot text-to-video retrieval, it achieves a comparable number to a state-of-the-art in a similar setting. So to conclude everything, we introduced the first end-to-end multimodal transformer that operates on raw inputs. We have a self-supervised pipeline to train this model end-to-end, and we introduce a modality agnostic transformer backbone for multimodal learning, and we achieve a state-of-the-art performance in downstream tasks. I would like to thank my collaborators at Google and also my PhD advisor at Columbia. And thank you for your time and attending my talk.
Thanks, Hansen, for the nice presentation. So if you have any questions, please feel free to post in Zoom chat, and we can ask in the end in the Q&A session. So the next paper is called Repetitive Activity Counting by Sight and Sound, and Yunhua will present the work.
This video presents the work Repetitive Activity Counting by Sight and Sound. The goal is to count how many times a certain activity happens in a video repetitively. Here are some example videos. The computer vision solutions to this challenging problem have a long tradition. Albeit successful, they could fail in poor set conditions, such as low illumination and occlusion. Our contributions are threefold. First, we address video repetition estimation from a new perspective, based on not only the sight, but also the sound signal. Then we propose an audiovisual model with the sight and the sound stream. Each stream facilitates each modality to predict the number of repetitions. Cross-model interactions are also developed for more accurate counting results. Finally, we introduce two sight and sound datasets for video repetition estimation. The sight stream adopts a 3D convolutional network as the backbone. It takes video clips as inputs and outputs the counting result for each clip. For the sound stream, we rely on a 2D convolutional network, which takes the sound spectrogram generated by the short-time Fourier transform as input and outputs the counting result in the same way as the sight stream. In this work, we first classify the current input into one of the repetition classes, and then take the counting result of that class as the counting prediction. We use both L1 and L2 loads for training. Since we don't have labels for the repetition classes, we propose to let the model automatically learn to classify by adding a diversity loss based on cosine similarity. Check our paper for details. Repetitions have various period lengths for different videos. Therefore, for each video, we propose a temporal stretch decision module to select the suitable frame rate to form video clips as the inputs, considering the features from both modalities. This is important, as video clips with small temporal stress may fail to include at least 2 repetitions, while too large temporal stress lead the network to ignore some repetitions. The reliability estimation module finally decides what prediction from which modality to use by estimating the reliability score for each stream and combining the counting results. See details in our paper. We introduced 2 audio-visual datasets for counting based on the Countix dataset. One is for audio-visual learning and evaluation. The other is for evaluating the benefits brought by audio-visual counting under various extreme set conditions. For our model, all modules matter, and the reliability estimation is preferred over simple averaging of sight and sound predictions. Each loss term lowers the counting error, and the diversity loss is important. On the extreme Countix-AV dataset, we can see that for harsh vision conditions, sound tends to have lower MAE than sight. Combining sight and sound always outperforms sight only. Here are some example videos and the predictions of our model.
Okay, go.
Ball. Mom, fail.
We can see that sound can play a vital role, especially under harsh vision conditions. We also compare our method with previous works. Our set model outperforms 2 recent state-of-the-art repetition counting algorithms in terms of MAE, and combining sight and sound shows further benefit in reducing counting error, especially in visually challenging settings. We have released our datasets and demo code. We also have collected a list of existing video datasets for convenient reference. Thank you for your attention.
Thanks, Junhua. So if you have any questions for this paper, please post in chat and we'll address them in the end. So the next paper is called ADA-MML, Adaptive Multimodal Learning for Efficient Video Recognition. So the presenter is Ramsva Panda.
Hi, I'm Rameswar Panda. I'm a research staff member at MIT IBM Watson AI Lab. I'm going to present our recent work on adaptive multimodal learning for efficient video recognition. Most multimodal video analysis methods are computationally expensive, as they usually process all the data, including redundant and irrelevant parts. Consider this video as an example. So this is a video of mowing the lawn. As you can see from the video, we ask a question: do all the segments require both RGB and audio stream to recognize the action as mowing the lawn in this video? The answer is no, because only for 3rd and 6th segment, RGB and audio are relevant for the action mowing the lawn. Whereas for the first and last frame, we don't need to process any of the modalities because they are highly irrelevant for those segments. So we can potentially skip those 2 segments for achieving the high efficiency. Similarly, for some of the segments, where only RGB is relevant, whereas for other, only audio modality is relevant. So our key idea is to propose an adaptive multimodal learning framework that selects on the fly optimal modalities for each segment conditioned on the input for efficient video recognition. So as you see from the figure, our approach optimally selects where to look and where to listen for a combination of RGB and audio to recognize the action of this video barking. To the best of our knowledge, this is the first work on data-dependent selection of different modalities for efficient video recognition. This one shows an overview of our framework. Our framework consists of mainly two networks. One is policy network, which is very lightweight, and recognition network consisting of different sub-networks, one sub-network for one modality. During training, we train both policy network and recognition network jointly using Gumball softmax sampling. And during inference, given a video, the policy network per segment wise, it decides which segment to use for achieving achieving high recognition accuracy as well as high efficiency. Our approach is can be extended to any number of modalities. Here we show three modalities: RGB, optical flow, and audio. Since optical flow extraction is computationally very expensive, we use RGB difference, which is basically difference of consecutive frames, to predict the location of optical flow, on-demand location of optical flow. We use a combination of efficiency loss as well as the cross entropy loss to train both of the networks. Regarding results, we do extensive experiments on 4 different datasets. Here we show results on RGB and audio combination on kinetic sound and ActivityNet dataset. While comparing to the NAV joint training baseline, which uses both of the modalities without any consideration of their relevance, they are highly computationally expensive, because they process all the modalities for all the segments, whereas our adaptive approach significantly reduces the computation by 47% on kinetic sound. Similarly, it reduces by 35% on ActivityNet. At the same time, it outperforms the baseline on both datasets. Similarly, for the other combination on RGB and flow on kinetic sound, our approach to while using flow in the policy network as well as RGB difference in the policy network outperforms the baseline in accuracy, as well as achieving significantly about 55% reduction in computation. Similarly, for RGB flow and audio combination, it reduces the computation by 55%, also achieve the best performance over the NAV joint training baseline. Overall, our approach obtains 35 to 55% reduction in accuracy while achieving better accuracy over the standard joint training baseline. Regarding some qualitative examples, as you see here, we saw qualitative examples for different combination of multi modalities. So first one is for doing fencing. As you see, our approach optimally selects RGB modality only for second and third segment, whereas doesn't select any audio modality because audio is irrelevant for this and noisy for this video. Similarly, for the case of playing piano, audio is selected for all the segments, whereas it only selects RGB for the second segment, leading to a significant reduction in computation. Similar observations can be made for both RGB and flow combination, also RGB flow and audio combinations. Our adaptive approaches focuses on right modalities to use per segment for correctly classifying videos while taking efficiency into account. Thank you. For more details, please see our paper titled ADA-MML, Adaptive Multimodal Learning for Efficient Video Recognition. Thank you.
Thanks, Ramspa. So the last paper in the invited paper session is called Space-Time Cross-dataset Improving Cross-Modal Video Representation Learning, and Mandela will present the work. And after this paper talk, we are going to have the live Q&A session. So if you have any questions for any of the 4 papers, please feel free to post in the Zoom chat area.
Hi, good day. My name is Mandela Patrick, and I'm a third year student at the VGG group. And today I'll be presenting research on audiovisual representation learning called Space-Time Cross-dataset, Improving Cross-Modal Video Representation Learning. And this is joined with collaborators at the University of Oxford and Facebook. So There's been a lot of recent works on multimodal video contrastive learning. Popular works include GDT, AVID, and XCC, and it's based on the idea of cross-modal learning, and you want a representation to discriminate between video and its corresponding audio. However, the problem with this multimodal video contrastive approach is that usually within modality, spatial invariances are not adequately learned. And so if you look at the loss function, the loss function has a weight for lambda VA and lambda AV, but no weight on lambda VV or lambda AA. The other thing we notice is that, particularly for video, high-level temporal information is discarded. So usually after the input is passed through the network and you get some sort of representation, it's usually just average pooled without any sort of mechanism to deal with the temporal information. And so we hope to fully exploit the spatiotemporal information to improve video representation learning. So our first contribution is feature crop augmentation. And this was inspired by a number of recent works such as Swab and Sinclair, which has shown that explicitly comparing differently cropped versions of an image improves self-supervised representation learning. However, this becomes computationally infeasible for video because the extra temporal dimension, the larger models, and the extra modality makes this computationally infeasible in both memory and speed. And so what we propose to do is to do cropping in feature space to get a large number of crops for within modality noise contrastive estimation. Our second contribution was to use a transformer for late temporal attention modeling. And so if you look at most video networks, X3D, R2 plus 1D, they all use spatiotemporal average pooling to get a fixed length feature vector representation. And so if the Res5 feature of these networks are part size by dimension, by time, by height, by width, we sort of naively average pool over space and time to get a fixed length representation, part size by D. However, we hypothesize that pooling in time is naive and propose to use a transformer for temporal modeling. And so we aggregate over time using a shallow transformer to get our feature vector representation. And so our proposed method, which we call STICKR, space-time crop and attend, we propose to take full advantage of the spatiotemporal information in video for self-supervised learning. And so compared to previous methods, which one mostly looks at cross-modal invariances, we look at within modality invariances by cropping in latent space. And then compared to previous works which average pools over space and time, we use a transformer to average over time to get our representation. And then we have the cross modal as well as the within modality self-supervised loss. And what we see is that our proposed feature crop improves upon cropping in the RGB space. So compared to 2 RGB crops or multiple RGB crops, and because of GPU constraints, we only can take 2 large RGB crops and 1 small crop. Our proposed feature crop outperforms other alternatives. We also see that the transformer works well for late temporal modeling. And so as we increase the number of frames, compared to global average pooling, which averages over space and time, our transformer sees improved performance as we increase the number of frames. And what we see is that our gains are complementary. So when we combine our feature cropping plus our transformer for temporal modeling, which is our STICKR approach, we see gains over just doing feature cropping or without the transformer. And then compared to the state of the art, at that point in time, here we see that our STICKR model outperforms alternatives, particularly the Cochlear state of the art model on both HMDB1 and UCF 101 fine-tuning video action recognition.
Okay, now it's the Q&A session for this group of 4 papers. So if you have any questions, please feel free to post in the Zoom chat area. So now I see some questions for the first paper for BATT for Handsome. So there's a question from Yuki. So for the question is VATT equivalent to MFV, but instead uses one shared backbone? So Hanson, do you want to answer the question?
Yeah, so do you have my voice?
Yeah.
Okay, thank you everyone for attending and also your questions. So the focus of our paper was basically utilizing transformers for multimodal understanding instead of just the learning pipeline. So we use MMV's learning pipeline and focus on how to deal with raw data, how to, for example, MMV operates on spectrograms, and also requires a huge amount of pre-processing for videos and also text. So we wanted to just make it end-to-end. So we focus on basically how to utilize a transformer, how to patch it, how to do the tokenization for minimal pre-processing in this pipeline. Also, there is something that I missed in the slides. So we also introduced drop token, which helps a lot on dealing with the redundancy. So drop token basically randomly drops just a portion of the data. So you have a low resolution, but it's not necessarily downsampling similar to other things. So the model gets, for example, 320 by 320 images and randomly drops certain portions of that image, and then gives it to the transformer for the rest of the model.
Cool. Yeah. So I think there's another question from Andrew. So for VATT, does using spectrogram instead of waveform improve the GPU efficiency? So can you train with fewer GPUs?
Yes, the short answer is yes. If you use a spectrogram, you might need less memory for training the model. But using the drop token, we saw that we get similar numbers and we also get similar training time. But the difference is big. You will perform on raw waveforms. Also, spectrograms, the way that we were doing it was online. So we were extracting a spectrogram online. So a spectrogram had a downside on the other side. So on the data pre-processing side. So we were using a huge amount of CPUs to do the pre-processing for this larger scale model.
Cool. So yeah, I think there is another question for Hanson. I think maybe it's already answered by the audience, but maybe you can confirm that. That'd be great. Yeah, I think for VATT, what is the training time? I think in the paper.
So
go ahead.
On version 3 is 3 days. I think at the time of writing the paper, version 4 was not publicly announced. So on version 4 is only 1 day. The same number of TPUs.
I see. Yeah, if anybody wants to ask any follow-up questions, feel free to unmute yourself to ask directly. And if anybody has any other questions for this paper or the other 3 papers, please post or just ask directly. Yeah, maybe I have a question for the second paper for Yunhua. Yunhua is here, I think. So I think I wonder, it's pretty cool. Yeah, you can use audio to count the activities. I just wonder, how do you filter out the sound that is not relevant to that activity? And do you study, have you looked at anything like per category results? So which category benefit most?
Yes. Categories such as playing ping pong or playing tennis, that kind of categories benefit most. And for other categories such as setup or sorry, let me think. The actions that do not make clear sound usually are not suitable for using sound for counting.
Yeah, that makes sense. Yeah, I think some categories might be makes more sense for counting. Yeah, some categories probably don't. Yeah, got it. if there are any, I'm not, if Rameswar and Manuel are here, yeah, if possible, you can raise your hands, but I'm not sure whether you are here or not. So if anybody has any other questions for this 4 papers,